Quadratic equations that can be factored across the integers are fairly simple to solve. Just as a quick review, we have a quadratic equation right here in front of us, 2x squared minus 4x minus 70. Set that equal to 0 so that we can actually solve it and factor it. The first step we remember is to take out the greatest common factor of all the terms if there is one. Well, I see that all of my terms, 1, 2, 3, are divisible by 2. So I'm going to pull out 2, leaving me with x squared minus 2x minus 35 equals 0. Now I'm looking at this trinomial. It's not a perfect square trinomial. There's no other pattern that I can use to quickly do it, so I'm going to use sum and product. I'm looking for two integers whose sum is negative 2 and whose product is negative 35. Those two integers are negative 7 and positive 5. So I can factor this, and it comes out as x minus 7 times x plus 5 times this 2 out front. And there we have a factored quadratic equation, and that can tell us that our roots are x equals 7 and x equals negative 5, and we determined that that was really helpful if we were going to have to draw this parabola. It's opening up, it has a root at positive 7 and a root at negative 5, and it looks something like that. And then we could find the vertex by finding the mean of these two x-intercepts, subbing that x value back into the original equation in order to find the y-coordinate, and we'd get a vertex here. But what happens if we get a quadratic equation that can't be factored over the integers, where the solution, x equals, isn't a whole number, like positive 7 or negative 5? Well, there's one other method that we can use, and it's called the quadratic formula. And what we're going to be learning today is also very much connected to these three diagrams that we're familiar with. The first, of course, having no real roots. The second having one real root. And the last diagram here showing a quadratic equation, a parabola with two real roots. Now the quadratic equation, or the quadratic formula, is going to be very helpful in quickly identifying whether or not it has 1, 2, or 0 real roots. And it can be done and used even when the factors are not integers, when it's not easy to solve. Understanding the quadratic formula has a lot of steps to it. So in this first investigation, we're just going to break it up into its individual steps so that you can get an idea of what's happening. Then we're going to derive the quadratic formula, which means we're gonna see how it was made and why it always works. The first thing we're going to do is consider the parabola of x squared minus 9. And we're going to solve this by first isolating x squared. So what does that mean? Well, we're going to solve. In order to solve it, we need to first set y equals 0, right? So essentially we're solving x squared minus 9 equals 0. And in our investigation, we're going to solve for x by first isolating x squared. What does that mean? Isolating means by itself. So we're going to get x squared by itself. And we're going to do that by adding 9 to both sides of the equation. So we're going to be left with x squared equals 9. Well, now we need to solve, right? So we're finding the value of x. So we're going to take the square root of both sides. So x squared, square root of that, is equal to the square root of 9. And it turns out there are two solutions here. X can either equal 3, or x can equal negative 3. 3 times 3 is 9, but negative 3 times negative 3 is also 9. Now we're going to do this exact same thing, but we're going to factor by finding the difference. So we're going to solve for x by factoring the difference of squares. So we're going to start with the exact same problem, x squared minus 9 equals 0. And this time we're going to solve by using our pattern. We know this is the difference of squares. This is a square value, and this is a square value, and here we have our difference sign. So my pattern tells me that I can just go x plus 3, x minus 3 equals 0, in which case the roots are x equals negative 3, because that will make this factor equal 0, which makes the whole thing equal 0, and x equals positive 3, which makes this factor equal 0, which would then make the whole thing equal 0. So So two methods to be used. The first was isolating x and then using square roots to find out that there are two factors. The second option was using our difference of squares technique, also gives us the exact same two factors, which means that x squared minus 9 has how many real roots? Two. Two real roots. The roots are -3 and +3, and we could see that on our graph right from the beginning. In part 2 of the investigation, we're asked to consider the relation y equals x plus 2 squared minus 9. And I've quickly drawn a sketch of the graph there. I see right away that this is in vertex form, which gives me my vertex at -2, -9. I don't know anything else about it, so some of these might not be in the right place. But that's a general idea of what this parabola is doing. And we're asked to solve for x. We know that the first step in solving for x is to set y equal to 0. So I'm going to go ahead and do that. 0 equals x plus 2 squared minus 9. Now when we're solving for x, what we're really doing is we're just peeling things away from x until we get x all by itself on one side and some numbers all by themselves on the other side. So all I'm going to do here is start peeling things away from x, and I'm using bedmass in reverse now as I'm undoing some operations. So the first thing I see that I can do here is I can add 9 to both sides, leaving me with x plus 2 squared on the right. Now this x plus 2 is glued together as one entity, and it's being squared. So how do I undo this squaring? Well, I could take the square root of both sides. The square root of 9 is 3, and the square root of x plus 2 squared is just x plus 2, but it could be positive x plus 2 or negative x plus 2. So over here I have 3, and over here I have plus or minus x plus 2. Okay, well let's split this into its two solutions, because this really is two different values. It's positive x plus 2 and it's negative x plus 2. So let's split it into its two. First we have 3 equals x plus 2, and over here we have 3 equals negative x plus 2. We'll solve this side first. We just subtract 2 from each side. That's going to leave me with x equals 1. And on this one, we have to notice that this negative sign is going to be distributed to both of the terms. Here we have 3 equals negative x minus 2. I'm going to add x to both sides. That's 3 plus x equals negative 2. And I can subtract 3 from both sides, leaving me with x equals negative 5. And now I have my two roots, my two solutions, my two x-intercepts, one at negative 5 and one at positive 1. And we've solved that. How many roots were there? 2. Investigation part 3 is also reaching back a few lessons to completing the square. And this is essentially how the quadratic formula gets derived. If you can complete the square, then you can understand how the quadratic formula works. So that's exactly what we're going to do in example number 3. Why don't you go ahead and try that on your own, and then check back in a few seconds to see how you did. So go ahead and pause the video, try that on your own. Okay, in order to complete the square, I'm first grouping my x terms, and I'm going to leave 16 outside of the brackets. Now I'm looking for half of b, and I'm going to square it in order to complete the square inside this bracket. So I've got x squared plus 10x. Half of 10 is 5, squared is 25. If I'm adding 25, I need to subtract 25 in order to maintain the same value, so that I haven't changed it. We said it equals 0, so if I'm going to add 25 to this side, I would need to add 25 somewhere else as well, or just subtract 25 from the same side. Well, now, because I want to be left with a perfect square trinomial, I can get negative 25 outside of the bracket. It's not being multiplied by anything, so it's fair just to move it over. Negative 25 plus 16 on the outside. And then I'm going to do these last two steps in one. Here I have my perfect square trinomial, which reduces to a squared binomial, x plus 5 squared. And on the outside I have negative 25 plus 16, that's going to be negative 9. And there we've completed the square, but we haven't solved yet. So now we still need to solve. So again, we're going to add 9 to both sides. It's going to equal x plus 5 squared. I can take the square root of both sides. Again, that's going to leave me with plus or minus x plus 5. So then our two options here are 3 equals x plus 5 or 3 equals negative x minus 5, because this negative sign would be distributed to both of the terms in the binomial. Here we are just left with subtracting 5 from both sides. We have x equals negative 2. Over here we are going to, last time we added x to both sides and then subtracted 3 from both sides. We're going to do it a little bit differently this time. This time I'm just going to add 5 to both sides. So I have negative x equals 8. Then I can multiply both sides by negative 1, which leaves me with just changing the signs, x equals negative 8. So there we completed the square and then solved, and we got our two roots. Again, they're integer roots, but it's helping us understand how the quadratic formula works. So just a recap of what happened here. We had a quadratic equation, which could be any old quadratic equation. We turned it into a completed square. So we completed the square on it, turning it into vertex form, and then we solved using square root of both sides. Now the question that you have before you is, will this work for any quadratic equation, or does it only work for some? To me it seems like it's going to work for any, but let's take a deeper look. At the top of the next page you have room for some notes. All we're going to do is define the quadratic formula. So, quadratic formula. This is a formula for determining the roots, formula for determining the roots of a quadratic equation of the form ax squared plus bx plus c equals 0, where a cannot equal 0, and we've seen that before. A can't be 0 because it would wipe out this whole x squared term, in which case it wouldn't be a quadratic equation at all, it would be linear. But this quadratic formula will work for determining the roots of a quadratic equation given in the form ax squared plus bx plus c, which is standard form, equals 0, where a cannot equal 0. And here's the quadratic formula. It tells us that in any situation, x is going to be equal to negative b plus or minus the square root of b squared minus 4ac, and that whole thing is going to be over 2a. We're going to derive this together to help us understand it, and then we'll go through a few examples where we use it, but you're also going to be required to memorize this. Thankfully, there's a catchy little song that helps us memorize it, and as embarrassing as it is to sing it on video for you to hear, I'm going to. I had a great high school math teacher. She was an older lady, and she knew exactly how embarrassing it was to sing this song in front of her students, but she still did it every year. And every time I use the quadratic equation, the quadratic formula, I still sing this song in my head, and I make sure I don't get this formula wrong. So here we go. Negative b plus or minus the square root of b squared minus 4ac over 2a over 2a. And you hear the catchy tune of Frere Jacques in there. We'll go again. Negative b plus or minus square root of b squared minus 4ac over 2a over 2a. And that's enough sing-song for the day. Let's see how this thing works. We are going to develop the quadratic formula using an example, so a specific quadratic equation that needs to be solved. And then on the other side, we're going to represent it just using ax squared plus bx plus c, the general form, and we're going to see that it works for every quadratic equation and what it's going to look like. You do not need to take these notes. You may if you like, but for working through the example in the general format and deriving the quadratic formula, you do not need to take the notes, but please watch the video carefully and try to understand what's happening and make some connections in your learning. Thank you. Enjoy. Our specific example is going to be 2x squared plus 5x plus 1 equals 0. And on the other side, we're going to be working with the general form, ax squared plus bx plus c equals 0. So here we go. Again, we're going to be working with completing the square. The first step in completing the square that we're going to first is get rid of this coefficient in front of the x squared term by dividing each of our terms on both sides by 2. That's going to leave us with x squared plus 5 over 2x plus 1 over 2 equals 0. And we're going to do the same thing on this side. We're going to divide each term by a. So here we're going to have b over ax, which is exactly what we had here, right? b over a, 5 over 2, plus c over a equals 0. Back to our left side. Now we're going to work on completing the square. So we're going to find half of b and square it. And we're also going to group our x terms. So we're going to do 2 steps in one. We're going to leave half on the outside of the brackets. Then we're going to take half of this and square it. So we're left with x squared plus 5 over 2x plus 5 over 4 squared, because 5 over 2 divided by 2 is 5 over 4. And if we add it, we need to subtract it. So we've got 5 over 4 squared. And then on the outside of our bracket, we still have plus 1/2, and it's going to be equal to 0. On this side, in the general case, if we're completing the square, we need to find out what half of b over a is. Well, that's just dividing it. B is divided by a, then we're going to divide b by 2, which is the same as dividing b by 2 over a. We're going to square that. If we add it, we need to subtract it. And on the outside of our brackets, we still have plus ca equals 0. So now on our left side in our example, we have a perfect square trinomial right here, but first we need to move this outside of the brackets. So we're going to leave our perfect square trinomial here. There it is. And we're going to move this to the outside of the bracket. So now we have minus 5 over 4 squared plus 1 over 2 equals 0. Jumping over to our general example, that means we're going to be left with x squared plus b over ax plus b over 2a squared. We're going to move this negative b over 2a squared outside of our brackets. Still have plus c over a equals 0. So it's looking messy and confusing, but we're just going step by step, being very careful, and you'll see what we reduce to at the end as we complete this square. So now, since we have a perfect square trinomial, we can represent this as a squared binomial, where we know the first term is a squared, so our first term is just going to be x in our binomial, and our second term is 2ab, and our last term is b squared. Well, look at what we just left ourselves with, b squared. So our second term in our binomial is just 5 over 4, and we are squaring that. And then we need to do a little bit of math on the outside of our completed square. We've got 5 over 4 squared. So that's 5 times 5 over 4 times 4, which is 25 over 16. And in order to add or subtract fractions, I need to have a common denominator. So I'm going to express half as a fraction over 16 as well. Well, half of 16 is 8. And that equals 0. We'll move on over to our general form. And again, we've completed the square. Now we're going to express our perfect square trinomial as a binomial squared. Our first term is x, and our second term is b over 2a. That's now a binomial squared. It represents all of this information. And on the outside, I'm going to be left with b over 2a squared, which is b squared over 2a squared. So b squared is b squared, and 2a squared is 4a squared. Plus, and now again, I want to be able to represent, if I'm going to add or subtract fractions, I need to have a common denominator. The common denominator here is going to be 4a squared. In order to get a common denominator here of 4a squared, I need to multiply the bottom by 4a to get 4a squared. And if I do that to the top, I need to do the same to the bottom. So the top gets multiplied by 4a as well, which leaves me with 4ac. Now my example in black has been encroaching on the space a little bit over here, but I'm going to try to shimmy it over a bit. And we're going to group our terms out here so that you see what we're left with. So here we still have our perfect, our binomial squared. And negative 25 plus 8 is negative 17 over 16. And 0 on the other side. Now in blue, we're going to do the same thing. We're going to keep our squared binomial. And we're going to group these together. So if I have a common denominator, I can just add the tops. Well, the top I'm left with negative b squared. And if this negative sign is going to apply to both terms, then I'm going to have minus 4ac over 4a squared equals 0. Now here's where we get to the part where we're going to be using our square root. So now we're going to try to solve for x. We're going to strip everything away and see what we are left with our x. So we still have x plus 5 over 4 squared. So we're going to add 17 over 16 to the other side, to both sides. And we'll do the same thing over here. So we're going to be left with our binomial, x plus b over 2a squared. And we're going to add this whole thing to both sides. b squared minus 4ac over 4a squared. Now remember, this sign isn't going to change now because this is considered as one big whole entity. I'm adding this whole exact thing to the other side. So that's why that sign didn't change at all. Good. And now you can see where the square root comes in. I'm going to take the square root of both sides, which is going to just leave me with x plus 5 over 4 on this side, and over here we're going to be left with plus or minus the square root of 17 over 16. Same over here, we're going to take the square root of both sides, leaving us with x plus b over 2a, and it's going to equal plus or minus the square of b squared minus 4ac over 4a squared. Well, as it turns out, if I take the square root of this fraction, I'll just draw this out for you so that you can see it. You don't have to write this, but this is the same as saying the square root of 17 over the square root of 16. Well, do you know what the square root of 16 is? Of course you do. 4 times 4 is 16. So we've got x plus 5 over 4, and this right side of the equation reduces. Sorry, you might have missed the last couple things that I said. I said this is the same as square root of 17 over the square root of 16. And we know that the square root of 16 is 4. So this reduces to plus or minus the square root of 17 over 4. Now in our general format, we're also left with a squared value under the in the denominator of this under the radical. So we've got x plus b over 2a, and that's going to equal plus or minus the square root of b squared minus 4ac over 2a, because 2a is the square of 4a squared. Well, it's getting a little bit more simplified here as we move along. Now to get x by itself, I just need to subtract 5 over 4 from both sides. So we got x equals negative 5 over 4 plus or minus square root of 17 over 4. And now we see we have a common denominator already. So let's see what happens when we group those together. Since they have a common denominator, I can rewrite this as negative 5 plus or minus square root of 17 all over 4. Let's move across. And this is starting to take form. This is the shape of the quadratic formula, right? So let's see what happens if we do the same thing on the other side. We've got x equals, we're going to subtract b over 2a from both sides. Still plus or minus b squared minus 4ac over 2a. And now since I already have a common denominator, I can rewrite that as one fraction, negative b plus or minus square root of b squared minus 4ac all over 2a. And there you have it, the quadratic formula. By completing the square on the general form, we get that in any quadratic equation at all in the form ax squared plus bx plus c, through a whole bunch of math and algebra, we've determined that x will always be equal to negative b plus or minus the square root of b squared minus 4ac over 2a. You do not need to know exactly all these steps, but you do need to memorize this guy, the quadratic formula. Well, thankfully, applying the quadratic formula is a lot easier than deriving the quadratic formula. Again, if I'm doing homework and I know I'm using the quadratic formula each time, I'm going to write it down at the top of my homework page. Negative b plus or minus square root of b squared minus 4ac over 2a over 2a. Now I can apply it. First I'm going to identify a is 2, b is 9, c is 6. This one's easy because all our values were positive, but if they were negative values, I need to make sure that I keep the negative sign with the value. And now I can just plug it right in to my formula. Negative b is negative 9 plus or minus square root of b squared, which is 9 squared, minus 4 times a times c, which is 4 times 2 times 6. That's going to be all over 2 times 2. And now we're just carefully performing some math on this. I want to find out what's happening under the radical sign, under the square root sign. 9 squared is 81. Negative 4 times 2 is negative 8 times times 6 is negative 48. 2 times 2 is 4. So we've got negative 9 plus or minus the square root of 33, that's 81 minus 48, all over 4. So these are the exact roots. So the exact roots are x equals negative 9 plus the square root of 33 over 4, and x equals negative 9 minus the square root of 33 over 4. But we can also find the approximate roots to the nearest hundredth by plugging this in our calculator, and we want to do so very carefully. My strategy usually is I'm going to plug in the square root of 33 first, then subtract 9, hit enter, and then hit divide by 4. So what I would do in the calculator is I would hit the square root sign, then I would hit 3, enter, then I would subtract 9. Your calculator will automatically store the answer to this, and then it will use that and subtract 9 from it. Hit enter again, then divide by 4. And if you do those steps in sequence, you will get the right answer. Some calculators, you need to input the 33 before hitting the square root, and it will do 33, then take the square root of that. That will work as well, and you won't need to hit that equal sign. But if you did that, you would find out that x is approximately negative 0.81, and x is approximately negative 3.69. And those are your two real roots to the quadratic equation 2x squared plus 9x plus 6 using the quadratic formula. In example 1b, we're given the equation 4x squared minus 12x equals negative 9. And right away I'm stopped because it's not in the right form. It's not in standard form. It doesn't have an equal 0 at the end. So I'm a bit stumped on how I'm going to apply my quadratic formula. What should I do in this situation? Well, of course, I should just add 9 to both sides, and then it will look exactly how I like it to look. And I won't have changed the value of anything. I've still got a true statement if I add 9 to both sides. Now I have standard form equals 0, and we're good to go using our quadratic formula. Now, what could also happen is that there could be a greatest common factor somewhere in here. There isn't. And I can't find any integers that will add to negative 12 and multiply to positive 36. So I'm going to go ahead and identify my parameters here. A equals 4, B equals negative 12, C equals 9. And now I'm just going to plug them into my quadratic formula. X equals negative B, so that's negative 12, which is positive 12, plus or minus square root of b squared, negative 12 squared, minus 4ac, that's 4 times 9. So we're going to be working with some big numbers here. All over 2a, which is 2 times 4. Well, let's reduce this step by step. We've got 12 plus or minus. Under the square root sign, we have negative 12 squared, that's positive 144. Any number that gets squared results in a positive number, negative times a negative. 12 times 12 is 144. Then I'm going to have 4 times 4, which is 16, and 16 times 9, which turns out is exactly 144, all divided by 8. In our next step, you're going to see what happens to the value under the radical sign. We have the square root of 0. So what number times itself equals 0? Well, it must be 0. So this plus or minus 0 is just nothing, and we don't need it anymore. 12 plus 0 is 12, and 12 minus 0 is 12. So the two roots here, or really, sorry, just the one root here, is going to be x equals 12 over 8, which reduces to 3 over 2, or you could represent it as 1.5, 1.5. So what did we notice here? Well, we noticed that under the radical sign, under the square root sign, we ended up with 0. And when we ended up with 0, we only had one root. So this equation only ever touches the x-axis. It has one root. And the connection is whenever the value under the radical sign reduces to 0, it's going to have one root. In this case, it's at 1.5. Often when you're given a quadratic equation and you're asked to factor it and solve and find the x-intercepts, you're also asked to sketch the graph by finding the vertex. Now we know that we can find the vertex because it falls on the axis of symmetry, which falls right in the middle of our two x-intercepts. So if we find our x-intercepts, let's say they're here at 2 and 6, then we can find the middle of those, which is 2 plus 6 divided by 2 which is 4, and then we could sub that value 4 into our original equation to get the y value, and that would tell us where the vertex is. But it turns out that just like the quadratic formula helps us to quickly find our x-intercepts, there's another little formula that can help us to find the vertex without ever finding the actual x-intercepts. And that's what we're going to take notes on now. So it's going to look a little bit strange at first, but here's what we learned so far. We learned that the two x-intercepts, when we use the quadratic formula, we end up with x equals negative b plus the square root of b squared minus 4ac over 2a, and the other root is x equals negative b minus the square root of b squared minus 4ac over 2a. And we know that when we normally find the vertex, the x-coordinate of the vertex, we're just finding the mean of our two x-intercepts. Well, here's an x-intercept and here's an x-intercept. And look at what happens when we find the mean of those two things. The mean is just adding them together. So we've got negative b plus the square root of b squared minus 4ac over 2a plus negative b minus the square root of b squared minus 4ac over 2a. And to find the mean of this for the vertex, the x-coordinate of the vertex, we are just going to add those up and divide by 2. Let's just focus on this numerator here. We'll leave the divide by 2 alone for a while. Let's just focus on the numerator here and see what happens to this if we actually add the two fractions in the numerator. Well, they both have a common denominator already. So we can rewrite them as negative b plus square root of b squared minus 4ac, and this plus sign is just going to mean we're keeping the signs the same. So we have negative b minus square root of b squared minus 4ac. And those are both going to be over 2a, and that whole thing is going to be over 2 still. Look at that numerator, what happens? That big ugly square root of b squared minus 4ac, well, we have plus one of them and minus one of them, so they just disappear. So at the top we have negative b minus b, well, that's negative 2b, divided by 2a, and that divided by 2. It's getting a little easier. The next step that we have is, you might not be able to see this right away, but if you had negative 2b over 2a, and you're dividing that whole thing by 2, that's the same as multiplying by 1/2, where we would go top times top and bottom times bottom. So what we're left here is negative 2b over 4a. Well, if we have negative 2b over 4a, we can cancel out these 2's in the top and the bottom, and we end up with a negative b over 2a. So the x-coordinate of the vertex of any quadratic equation is found by taking negative b over 2a. I'm going to erase this work and just draw a quick sketch to help you understand what just happened. So, basically what we've said is that we can have any parabola in the whole world. Let's say it looks like that. And we will know its x-intercepts by using the quadratic formula. One of the x-intercepts is negative b plus the square root of b squared minus 4ac over 2a. And the other one occurs at negative b minus the square root of b squared minus 4ac over 2a. and the vertex happens to be along the line, axis of symmetry, which is found by x equals negative b over 2a. So there's in summary what we've discovered so far today. And this works really well because sometimes we can't factor our x-coordinates. We can't factor and find our zeros over the integers. They use decimal numbers and fractions. And so this quadratic formula will get us the right answer every single time if we apply it correctly. And the vertex is even quicker and easier to find. Negative b over 2a. Let's try a few examples with that. Okay, we're going to apply what we've learned in example 2. So find the x-intercepts and the vertex and the equation of the axis of symmetry of the quadratic relation y equals negative x to the power of 2 plus 8x minus 3, and then sketch the parabola. So in order to do this, I first need to solve the equation by letting y equal 0 and then use the quadratic formula. So what we're going to be left with is negative 5x squared plus 8x minus 3 equals 0. I'm setting y equal to 0 because that's what I need to do to solve this. Solve means find the values of x when y equals 0, or find the x-intercepts. And we know the x-intercepts occur when y equals 0. And there's no quick, easy way to factor this, so I'm going to use my quadratic formula. First, identify that a equals negative 5, b equals 8, c equals negative 3. Then I'm going to go ahead and plug these numbers into my quadratic formula, which is x equals negative b plus or minus the square root of b squared minus 4ac over 2a. You, of course, used the song that we learnt together. Such a wonderful song. And here we go. Let's plug it in. X equals negative b plus or minus square root of b squared minus 4ac all over 2a. Let's reduce this. We've got 8 equals negative 8 plus or minus the square root of 8 squared is 64. And then my three numbers here, I'm going to multiply them together numerically, but then I'm also going to keep in mind that I have a negative, negative, negative. So a negative times a negative is going to be a positive, times a negative is going to be a negative number at the end. So here we have 4 times 5, which is 20, times 3, which is 60. And you're looking at negative 60. That looks like a nice number. And 2 times negative 5 is negative 10. So let's reduce this one step further. We've got negative 8 plus or minus the square root of 4 over negative 10. And I'm going to go ahead and split this up into its two x-intercepts. Now I've got negative 8 plus square root of 4 is 2 over 10, negative 10. And I've got x equals negative 8 minus 2 over negative 10. So our roots are negative 8 plus 2, that's negative 6. Negative 6 over negative 10. Negative over a negative is a positive. 6 over 10 reduces to 3 over 5, or 0.6 for you decimal lovers. And here we have negative 8 minus 2, that's negative 10, over negative 10, that's just 1. And there we have our two x-intercepts. Now to find the x-coordinate of the vertex, I could use the old way. I'd go, 1 plus 0.6 divided by 2 is 1.6, divided by 2 is 0.8. So the x-coordinate of the vertex is at 0.8. But if I haven't done all this work already, that becomes a little bit difficult. So we're going to apply our new formula for the x-coordinate of the vertex in order to find that. So we found that for the vertex, the x-coordinate is equal to negative b over 2a. We'll sub in our values. Negative b is 8, a is negative 5, equals negative 8 over negative 10, which equals 0.8, or 4/5. And how do we find the matching y-coordinate for our vertex? Well, I just take my 0.8, sub it back into the original equation, perform some algebra, and we'll come out with the answer. I'm going to go ahead and do that right now, and I'm going to erase this side to do it. So we're taking our x-coordinate in order to find out what our y-coordinate of the vertex is, so we're still working on the vertex here. We're going to take negative 5 times 0.8 squared plus 8 times 0.8 minus 3 and find out what that equals. Well, I'm going to use BEDMAS. I have to deal with my exponent first. So 0.8 times 0.8. Well, if 8 times 8 is 64, then 0.8 times 0.8 is 0.64. Here we have 8 times 8. It's going to be 6.4 and minus 3 at the end. An easy way to do this would be to carefully chuck the whole thing in your calculator, but I just want to multiply it out for you so that you can see it. Negative 5 times 0.64 is negative 3.2 plus 6.4 minus 3. When we put those all together, we get 0.2. So, the vertex is found at 0.8, 0.2. We have both of our x-coordinates. They were our x-intercepts, where x equals 1 and x equals 0.6. And now we can sketch a graph of this parabola using information that we have. We can make this equal, let's make 1 right there, negative 1 there, and 1 right there. So we're out here at 0.8, 0.2. We've got an x-intercept at 1 and an x-intercept at 0.6. So here we have the point 1, 0. Here we have the point 0.60. Here we have the point 0.8, 0.2. And we're going to label our graph y equals negative 5x squared plus 8x minus 3. Lovely. We've sketched our parabola by first finding our x-intercepts, then finding our vertex, and then drawing a careful graph. This is example number 3 from lesson 6.4 using the quadratic formula. Between example 1 and 2, we were able to see parabolas that had 2 roots or 1 root. In this case, we are going to connect a parabola that has no real roots. So we're given the parabola has an equation y equals x minus 2 squared plus 3. And we are going to state the coordinates of the vertex, which we can get easily because it's already in vertex form, the equation of the axis of symmetry, and the direction of opening. And all of these things we can get without doing any calculations. After that, we'll look at B. We're going to determine the x-intercepts, and we're going to verify using the quadratic formula, and then we will sketch the parabola. So the parabola that we are given is already, the equation is already in vertex form. So our vertex, we can right away just say, is h and k. So our vertex, the x-coordinate is 2, the y-coordinate is 3. For the axis of symmetry, well, the axis of symmetry is the line x equals, and it goes through the vertex. So the vertex is at x equals 2, so the line of symmetry must be x equals 2. Again, that's the line that goes right down the middle, crosses through the vertex, and since our vertex is at 2, 3, our axis of symmetry must be x equals 2. Direction of opening, I look in front of my brackets here, my squared binomial. Coefficient a is positive, it's positive 1, so this opens up. B of example 3 asks us to determine the x-intercepts. Well, just a quick look at the sketch over here. This is the sketch of our parabola. If the vertex is at the point 2, 3, and the parabola opens up, does it ever cross the x-intercept? The answer to that, of course, is no. There are no x-intercepts in this case. There are no X-Intercepts. Now that's not quite sufficient, doing it by the graph and just judging it by the equation that we're given. So we're going to verify that using the quadratic equation, the quadratic formula, and we're going to find out what happens. So in order to use the quadratic formula, first of all, this needs to be rewritten in standard form. So let's do a little bit of math on this. This is a binomial squared, and I know that that expands to be a squared, and over here we're going to have b squared, and in the middle we're going to have 2ab. So we're going to have minus 4x, and on the outside we still have plus 3. I can combine like terms, leaving us with the parabola in standard form, x squared minus 4x plus 7. Well, now that I have this, I know my parameters. My coefficients: a is 1, b is negative 4, c is 7, and now I can go ahead and plug them into the quadratic formula. Negative b plus or minus square root of b squared minus 4ac over 2a over 2a. It's a tough decision when a teacher has to sing on video something that won't be destroyed. Okay, the beauty of the quadratic formula is that I just need to take my parameters a, b, c and plug them in, and I will get the solutions for this equation. So negative b, well, b is negative 4, so I have negative 4, that's positive 4, plus or minus the square root of b squared. I want to make sure I keep this negative 4 in brackets. The negative belongs to the 4, so there negative 4 is going to get squared, minus 4ac. And that's all getting multiplied together over 2 times 1. Let's quickly simplify the easy stuff here in this bracket. We've got negative 4 times negative 4, which is positive 16. And we're going to have minus 4 times 1 is 4. 4 times 7 is 28. And this is over 2. Let's reduce what's under the square root symbol here. 16 take away 28 is negative 12 over 2. Now, I've run into a problem. You can see under the square root is a negative number. There is no such thing as the square root of a negative number. There is no number whatsoever that can be multiplied by itself to equal negative 12. Can't happen. So this is undefined, and there are no real roots. If there are no real roots, there are no real roots, period. Therefore, there are no X-intercepts. Now, we already knew that, but it was good to verify using the quadratic formula, and now we know what to identify. If we're using our quadratic formula and we ever end up under the square root with a negative value, we can be certain that this parabola will not cross the x-axis. The last part of the example here is to draw a sketch of our parabola. We've noted a couple things already, that the vertex is at 2, 3. So go ahead and put that on my graph. I know it opens up, so I will label it down below. It does open up, but we haven't talked about where it crosses the y-axis. It does have a y-intercept, and it's pretty easy to find out where that is. The y-intercept happens wherever x equals 0, right? So if we're looking across our x-axis, wherever x equals 0, well, that's where the parabola is going to cross the y-axis. So let's find out what happens here. What value of y will we be at when x equals 0? So I can just sub in 0 for x. Inside the bracket I now have negative 2 squared plus 3. Negative 2 squared is negative 2 times negative 2, that's 4 plus 3, 7. So therefore, the y-intercept is 7. And I can go ahead and plunk that on my graph. That's also very helpful because I know that parabolas are symmetrical on both sides, and I know they're symmetrical over the axis of symmetry, which occurs at the vertex. So I know that if I go 2 units to the left of the vertex, and I'm at 7, then the value of the parabola will also be 7, 2 units to the right of the vertex. So if the point 0, 7 is on the parabola, and my vertex has an x value of 2, then the point 4, 7 must also be on the parabola due to the symmetrical characteristics of a parabola. And I can go ahead and sketch it, making sure I have a rounded bottom. Of course my sketch isn't perfect, but it's not bad. And there you have it, with our vertex labeled, our 2 other points that helped us draw the curve, and again, no x-intercepts in this example. Throughout this unit, we've talked about applications of quadratics and quadratic equations. One of them is to model the path of a projectile. So in example 4, we're looking at the path of a basketball. After it is thrown from a height of 1.5 meters, so someone has tossed it from a height of 1.5 meters above the ground, it follows the path given by the equation h equals negative 0.25 d squared plus d2d plus 1.5, where h is the height in meters and d is the horizontal distance in meters. We have 2 tasks. We need to figure out how far the ball has traveled horizontally to the nearest tenth of a meter when it lands on the ground, and we need to find the horizontal distance when the basketball is at a height of 4.5 meters above the ground. So first, A. Okay, let's think about the parabola that will be made by the path of this basketball. We know that there is going to be ground level. Somewhere there's going to be ground level. And so when the parabola gets to here, well, right there it's hitting the ground, which tells us that it's going to hit the ground at an x-intercept. We don't know where it starts. I'm going to guess he tosses it up a little bit, and this is going to be our height of 1.5 meters, where it all starts from. So our goal is to find our 2 x-intercepts. There's always going to be, well, there's not always going to be 2, but in this case there is going to be 2, but one of them is going to be irrelevant. Of course, the one behind the person who throws it. This one doesn't actually exist in this real life situation because our friend is throwing the ball from right here. Well, if the ball is going to hit the ground at our x-intercept, that's when the height is 0. So all I need to do is set h equal to 0, rewrite the right side of the equation without changing anything, and then solve. I notice right away that I have a negative decimal out in the front here, and I have a decimal in the back. These things aren't going to factor out all that nicely, so I'm going to just go ahead and use the quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac over 2a. I know my parameters. A is negative 0.25, b is 2, and c is 1.5. So now all I need to do is plug those numbers into the quadratic formula, and I will get my 2 x-intercepts, one of which will be a real answer, one of which will not be, but we'll talk about that when we get there. So x equals negative b, that's negative 2. plus or minus the square root of 2 squared minus 4 times, and I know this is 1/4, and I'd rather work with fractions, so I'm just going to go ahead and rewrite that as negative 1/4 times, and this is 1.5, which is the same as 3 over 2, all over 2a. So 2 times negative 1 over 4. We can reduce this by multiplying some things together here. We've got negative 2 plus or minus the square root of 2 squared, which is 4, minus 4ac. So we have 4 times 1/4. Well, that ends up being 4 over 4, which is 1. And we have minus a negative number times a negative number, which is a positive number. So I have positive 1 times 3 over 2. Well, let's go back to doing a decimal here because it came out pretty nicely as 1.5, 3 over 2. And here we are left with 2 times negative 1/4. So that's negative 2/4, which is negative 1/2. And we can reduce this further. So we have negative 2 plus or minus the square root of 5.5 over negative 0.5. So this tells me that d, if I plug this into my calculator, d equals negative 2 plus the square root of 5.5 over negative 0.5, or d equals negative 2 minus the square root of 5.5 over negative 0.5. Now I can't eliminate one of my answers yet. I really should just plug them both into my calculator and then figure out which value of d makes more sense. So this first one, if I plug it into my calculator, reduces to approximately negative 0.7, and this one over here reduces to approximately 8.7. Now remember, our question was how far has the ball traveled horizontally when it lands on the ground? Well, it wouldn't make much sense if we had a negative value for the horizontal distance traveled before it lands on the ground. We're clearly progressing here in a positive fashion. So the final answer is the basketball has traveled a horizontal distance of about 8.7 meters when it lands on the ground. In the first part of this example, we had to find the value of d when h was 0, when the height of the ball was 0, when it had reached the ground again. But in the next question, we need to find the horizontal distance, so we're still finding the value of d, not x, finding the value of d, but this time when the basketball is at a height of 4.5 meters above the ground. So this time when I sub in, I'm not going to sub 0 for h, I'm going to sub 4.5 in for h because I want to find out what d is. I want to find out what d is when h is 4.5. So the right side of my equation doesn't change just yet, 1.5. But this isn't in the form that we're used to putting in the quadratic equation, the quadratic formula. In fact, this won't work. If I plug in the same numbers as before, I'm going to get the same answer as before. We need to have this set equal to 0. In order to do that, we need to subtract 4.5 from both sides of the equation. I'm a little bit tight on space, so I'm just going to erase this. 4.5 minus 4.5 is 0, and 1.5 minus 4.5 is negative 3. So now I have a new equation that I can plug into our quadratic formula, and when I use this one, I will get the values of d where the height is 4.5 meters. Now because a parabola is symmetrical, it's likely that this is going to happen at 2 separate points. But we'll see what happens as we carry on. Alright, A is negative 0.25, B is 2, C is negative 3. And I can go ahead and sub those into my quadratic formula. So we have negative b, which is negative 2, plus or minus the square root of b squared, which is 2 squared, minus 4ac, all over 2a. Let's reduce what we can. Inside the square root, we have 2 squared, which is 4. And then we have 4 times a quarter, and they're both negative, so that's going to be positive 1. Positive 1 times negative 3 is minus 3, all over 2a. 2 times negative 0.25 is negative 0.5. And I'm still using x. We know that in this case x is being replaced by d, so d equals these things, d equals these things. So when we're finding x here, for this application, it's actually the horizontal distance, which is represented by d in this problem. So here we have our two answers. I can reduce this under the square root. 4 minus 3 is 1. The square root of 1 is 1, because 1 times 1 is 1. So we have two options here for d. Either d equals negative 2 plus 1 over negative 0.5, or d equals negative 2 minus 1 over negative 0.5. Over here, we get negative 2 plus 1, that's negative 1, over negative 1/2, well, that's positive 2. And over here, we get negative 2 minus 1, which is negative 3, over negative 1/2, which is positive 6. So the horizontal distances, when the ball is at 4.5 meters in height, is 2 meters and 6 meters. So our sketch is not to scale here. 1.5 is here and 4.5 is here. So that's not quite right, but it does show us where these things happen. This happens at 2, and this happens at d equals 6. I hope that this helps in doing your homework this evening, and please come to class with questions, and also be prepared for your quiz.